many of the things that you see in chapter 11, or many of the, let's say, the worked versions of problems in chapter 11 and the diagrams that they are using to show you how things work, take the form of control step responses. So we have an interesting question, which is, how do I obtain such responses given perhaps just a description of a system and a controller? And what I saw yesterday is that many of you do not have clearly in your mind what I would regard as a well-developed strategy for simulating systems. So I want to talk about the things that you were supposed to have learned in CPN first, in terms of how do I simulate systems. And I want to remind you that when we were in CPN, we covered this notebook over here. This is a notebook that was in last year's section of the repository, and you will recall that we spoke very broadly about a number of different ways in which you could obtain, or in which you could obtain the response of a system given changes in the inputs. And the first way, the really low down basement level version of simulation, the one that you were supposed to understand the best because it is the most understandable in terms of the actual steps that are happening, was the idea of simply doing a very normal or a very simple Euler integration yourself. Okay? So you can see what's happening here. I have here a first order system. These are the differential equations that correspond to that transfer function. This particular equation over here specifies the derivative, or shows how you would calculate the derivative. Here I have what should be to all of you an incredibly familiar looking loop, which is an Euler integration loop, and I'm simply calculating that derivative. And this part over here, this piece of code there, is actually doing, well, let's say the whole thing is calculate the derivatives, right? Calculate the new value of the thing that I'm integrating using the Euler update formula, and then there's some bookkeeping where I just append that to a list of y's that I can plot later. Now, every system you've ever seen in CPB would be perfectly suited to that kind of approach in terms of, if you ask the question, but how are they plotting diagrams that look like this, right? How does that happen? They say that they're simulating this with the PI controller, and they've got some kind of a function, transfer function that they, at least on some level, nobody here should imagine, like, I don't know how to do this. At the base level, you all know how to do this because you would find the differential equations, you would plug it into an Euler integration loop, and so on. What a lot of you, I believe, have taken from the further down parts of this is lots of code, very little code, right? And that's the big message, is like, I will always use the small code above the big code, and I will always use, and there's this other level of understanding, which is like, this is a lot easier to understand from the user interface level. I think I've spoken about this before, right? Like, I had this really favorite cartoon. When I was younger, I read the Archie's cartoons. And there was this one character who was like a prototypical geek with like glasses and everything, and there was like a prototypical football player called Moose. You know, and so Moose is like, how does this TV work? And the geek guy is like, oh, no, you know, it's like all electron beams and plates, and, you know, they have a signal that comes through the air. And Archie's like, Moose, this is how it works. You press this button and that's how it works. And I love that little scene because it gives a very good view on these two levels of like, how does it work? And also like on understanding. right? If I say, do you understand how your TV works? There are those two answers, right? Like, do you understand how your phone works? There is, do you understand all the stuff that makes up your phone? That's the one version of the question. And then there's the other version of the question of like, do you know where the button is that turns it on? Do you know what actions to do in order to send an email, right? Those are very different levels. And what I do acknowledge is that the Euler integration loop, that's easier, it's easier to understand how that works on the first way, right? Because it's a lot simpler in terms of the things that it is doing is very simple, right? It's a for loop, it's doing Euler integration. But it's harder to understand from a user interface level because it's not actually a user interface. If you're treating this as a user interface, it's hard because I have to like know a lot of things. I have to know a lot of things about how the moving parts work in order to assemble a functioning solution. And so I understand why. So because I want to make this clear. By no means there's no levels here, right? But I understand why people are drawn and why I'm drawn to like those simple solutions. Now, the first thing I want to say is that all of these things, all of the stuff below the Euler integration loop, and I think I made it clear last year as well, but I just want to kind of remind you of why did we ever, if control.step exists and control.lsum exists, and SymPy or scipy.signal.lsum exists. Why am I ever showing you this for loop? And the answer, it's not very interesting, but none of the libraries that I know of that are in the Python ecosystem support the simulation of systems with dead time. That's the complete answer. If your system and your controller and your valve and all of those things do not contain dead time, it is possible for you to obtain an LTI object that represents the closed loop transfer functions of your system. And the challenge is that obviously this is much, much easier, like I say, from a user interface point of view. It's a lot more conceptually simple to say, well, G, quote unquote, is my system. And through magic, hidden from me within scipy.signal, if I invoke just this one word, I can magically get the step response. Actually, that's weirdly easy to understand, right? Because it's an interface. Press this button, the step response comes out. So that's a lot simpler. And honestly, I would actually have loved if we could do that for all of the stuff in the subject, but we can't because it doesn't. Because there's no space in an LSUM object, right? So here we have the LSUM version of this, right? I've created a G object, which is a scipy.signal.lti object. And look how easy that is. Isn't that amazing? Couldn't it be that way for all of our stuff in TC Lab, right? Like we have this thing, it's called a G object. If I want the step response, I do G.step. If I want the impulse response, I do G.impulse. If I want the response to arbitrary stuff, I do G.lsum. Couldn't it just be that simple? And so, just from a very basic level, I want you to understand why, firstly, just understand at least part of the decision-making process that clearly these designers of these libraries are involved in. And then I want to take you through my solution of this, because I honestly don't want you to work harder than you actually have to. I value understanding, but I also value ease of use, absolutely. So just like I freed you from having to calculate your own Ruth arrays, I hope to free you from having to write your own simulations using Euler integration. But I want you to understand that there's something very special about systems that contain dead time in the feedback loop. And specifically, if you think about the kind of the most simple version of a control loop that we've come across, right? So this is now, let's say we've got our GC, we've got our GP. If you think about what the LTI systems how they are represented in all of the systems that we know in Python, right? So we know of two big systems in Python that allow us to handle LTI systems in this kind of effortless way, right? So we've got scipy.signal .lti, and we've got this control library which supplies this TF method. And both of those objects are constructed from a numerator, a denominator, actually only those two things, a numerator and a denominator list of coefficients. Okay, and so what that means is that all of the objects that can be represented in that way, if I tell you, here is a list of numerator coefficients, here is a list of denominator coefficients, all of them look like rational functions, so they'll be like a s squared plus b s plus c over, 3s to the 3 plus 5s plus 1 or whatever, right? So all of them, they look that way. Now, do you notice that firstly, in neither of those libraries is there even the opportunity of representing delay. So just from a very practical point of view, this is why I'm saying this is not part of the lecture material, right? It's not in the textbook because this is kind of really a practical Python thing. And it could be otherwise, right? This is not like a law of nature. The library writers could have added support for delay in these functions, right? They could have just added a third argument and had it give you a delay. No problem, right? But the problem, behind the problem is that they want to be able to represent, so the mathematical word for the concept that I am going to reach for here is called domain being closed. And so the rationals are closed under or they form a closed algebra. What that means is if you add two rationals together, you get a rational. If you multiply two rationals, you get a rational. If you divide two rationals, you get a rational. You don't get some other weird thing, right? You don't get something that is not like that thing at all. You get something that is of the same kind, but just has different lists of coefficients. Okay? There's a problem when I add systems into this mix which have dead time, because I can take a system like this. If I add that to a system like this, that sum can no longer be represented in a form that resembles either of those forms. So you can imagine, okay, here I've got like a rational multiplied by an exponential. Okay? And here I have a rational. And the sum of a rational multiplied by an exponential plus a rational doesn't look like a rational multiplied by an exponential at all. Is this making sense to everybody? Let's make this. I'm just going to, because I suck at this kind of math, I'm going to make the math a bit easier. I think the easiest way to make it easy is like this. Okay, so now at least the math is easy to do, right? So if I have them on the same denominator, then it's super easy to understand that the sum of that is going to be 2e to minus 3s plus 1 over s plus 1. And do you see the problem? Because now it's like, you tell me now the coefficients, the constant coefficients, right? Like the known numeric, like 5 and 2, set of coefficients that form the numerator and the denominator of that new thing. It doesn't exist. So right now, as soon as you add that e term in, I've kicked out the knees of all of the numeric simulation stuff that's easy to use within the Python universe. Because now I can't use the control library. I can't even use, the control library does not even allow me to represent that sum. In fact, it doesn't even allow me to represent like the components of that sum, right? Like I can't even, there's no syntax for me to build one of these in the control library or the LTI library. So what I could do, and this works for low order systems, is I could simply use SymPy. And I could use SymPy for all of my calculations, and SymPy doesn't care. But the problem is, there's like a downstream problem. SymPy can do these calculations just fine, but it's limited in the amount of inverse Laplace foo that it has, right? So it can only do certain inverse Laplaces, right? So I could do this code in SymPy, but I would find it impossible to invert that Laplace transform. Well, maybe that one because it's pretty simple, but like if it gets a bit complicated, and as you may have kind of learned, in frustratingly unpredictable ways, SymPy will reach some kind of limit to its abilities. Right, so exactly the same code will work fine for some kind of low-order system, and then you choose a coefficient to be 0.7, and everything breaks, which obviously is not optimal. Okay. So, right. So what's the practical solution to this? There are two broad classes of practical solution. The one solution, which is the solution that the textbook takes, is to use a more powerful simulation environment. So you'll see that the textbook uses Simulink, and you've heard me talk about Open Modalica before, and you can very simply build systems, including systems that feature delay, within Open Modalica and press play and get the answer. So that's option number one. If you and from a user interface point of view, that's probably the most satisfying version, because you get this nice symmetry where the thing that you're building looks just exactly like the picture in the textbook, right? So I just want to remind you what these diagrams would look like. So in Modalica, the key parts are, we're going to spend pretty much all of the linear modeling stuff that we do, all of the blocks that you're going to need to do the kind of stuff that you do with block diagrams are found in this blocks area over here. Okay? Just to build one. Okay, let me just build one. I have like a very nicely edited down version of exactly what I'm going to do now already on ClickUp. I'll post it for you so you don't have to like watch me go through this. But you'll see it's actually like if you kind of had gone through the process at least once, it's really straightforward. So let's say I'm going to simulate a first order system under PI control. It turns out that as many of these kind of systems, Modalica already contains blocks, as I've mentioned a couple of times before. Like these things are so common that there'll be a block in the environment that you're using, right? Now, because Modalica actually uses differential equations, the PID is not an ideal PID. It's a realistic PID with a first order filter, just like the one that's in the ISA realizable form in your textbook. So let's use that one. So we can use PID. So I'm going to grab that, and I'm going to grab a first order system. You can actually zoom in a bit on that, make it a bit easier to use. So you can build exactly that loop, and of course the problem that we are encountering most of the time is this problem with dead time. The dead time finds itself under nonlinear. So like a first order plus dead time system in Modalica, you'd simulate that by adding this fixed delay block on there. So you'd link that to that, and this to this. I'm not even really, I should have actually timed myself. How long does this take? There's a feedback block directly in math. And so you can do basically exactly the same thing that it can look exactly like the diagram that you're trying to simulate. So let's do a step response. Right, so there's a step. So that's going to do a step in the reference, going into this controller, going into a first order plus dead time, and going all the way to the feedback loop over there. So I've now built my diagram. I'm just going to put in parameters. So you'll see it's got default parameters here. I'm just going to choose some kind of gain, some kind of tau I, some kind of tau D. This is not like I'm really just I'm just making stuff up. I'm not like trying. There's no clever tuning rules involved here. First order system, I'm just going to go kind of in the same order of magnitude as you kind of want that product to be around 1, right? So let's make that like that. And let's add some like significant delay, like a 10-second delay. And basically we're ready to rock and roll at that point. So we can press play. It's going to ask us to save it wherever. Actually, just remember that the default stop time on these simulations is like super small because it's built for mechanical systems. So our systems typically take a little longer. So I'm going to do like 100 seconds. Well, no, wait, that time constant was like 100, right? So like I'll do 1,000. Okay, so now we're ready. So the thing that we're trying to look at, the Y that we're trying to look at is this Y over there, and there's now your step response of the. If I want to also plot the reference signal, I just can add that there. So there's my step response, PID control, first order plus dead time system. Okay? And look at that, like I've still got lots of time left in the lecture. Okay? So, I mean, if you just want to get a quick read on stuff, and if you read through the chapters in the textbook, you will see that this is exactly the method that the textbook recommends. Right? The textbook says, open up your graphical modeling environment, draw out this diagram the way that it is over here, using the blocks in your graphical modeling environment, put in all of these different parameters, press play, and see the result. If that is all you want, if you just kind of want to see what the output looks like, that's perfectly fine. So I'm going to remind you of two specific things. So the reason why I dislike this for some of the other stuff that we're going to be doing is that there's a bit of a like a missed handover between Python and Medallica. So it's not immediately clear how you would run this. And for instance, let's say we were trying to do our first order plus dead time simulation that we were doing yesterday, where I had a function which was parameterized with these k's, right? And I could say, okay, so this function will, if I just give the k, and I can plug that into other functions. I can use scipy.optimize.minimize to go and find those optimal parameters, right? That was hugely beneficial, hugely useful to me, to be able to build the diagram with code instead of having to build it by hand and double-click somewhere and then press like a button or whatever. Because scipy.optimize.minimize is running that code like, I don't know, 100, 1,000 times. You don't want to be the guy like responsible for clicking and opening and setting the K and then pressing play and then like jotting down on a notebook. Yes, okay, that was 5.2. Right, and then keep going. Nobody wants to be that guy. So there are problems. The other way is actually not as hard because right here on the simulation output window, there's this CSV output button. And so if you have something that you have simulated in Medallica, you just click that button and you can get a CSV. And then you can open it in Excel and plot it, or you can open it in Python and plot it, or whatever, right? But you can't go back. So there's no easy way for you to write a Python program that produces a Medallica. Well, I mean, there are ways, but there's no easy way. Okay? And I want to call your attention just to a couple of things here. That notice that it is actually doing real dead time here. So Medallica is not doing or the simulation engine is not doing any approximation of the equations. It's using a pure transport delay. The way I can see that is it's got this nice, crisp, immediate output there, right? Some of you who were playing around with Parday approximations would see that if I were to approximate this dead time with a Parday approximation, that response would not be crisp, it would be smooth. Why? Because we have this high order response. Is that making sense to everyone? You're talking about methods, lots of methods. Sometimes it's open Medallica, sometimes it's sim-lsim, sometimes it's step, sometimes it's the control function, sometimes it's scipy.sig, right? You just tell me the one, if I have memory only for one method, and I want the one method that will always work, what method will that be? This is the one that's on your screen right now. Okay? This is the one that will always, always work. If you choose small enough time steps and you understand how this integration method works, you can always build a relatively good simulation of the systems that you're working with. And this is why you will find that you have those projects from previous groups, right? This is why you will find that you don't need to take a picture of this. I'm literally recording this, and it will be on YouTube. Not only that, this is not hidden knowledge. It is like the notebook from CPN. So you can copy and paste it from the notebook. Now, and also even like that Medallica thing, the nicely prepped video is way better than my demonstration was. Okay, so this is the one that always works, but I understand the problem is that this one is not as user-friendly. And so I have developed, let's say am developing, or actually let me just, before I go to that, I want to remind you of, let's say, the more full version. So this notebook here, I think some of you may have overlooked because it's not in the actual control section, but it's under the simulation heading in the table of contents. So if you go to the table of contents on there's this whole section over here which is simulation, okay? And in that section I have this whole thing about hybrid system simulation, and this takes you through the for loop based version of, at this point I'm simulating a PI controller. Now, the reason why I don't actually regard this as part of the subject is that there is literally nothing new in this for loop if you understand how the previous for loop works. Okay, what's happening here? I'm calculating derivatives. I'm calculating here the derivatives that are associated with the states of the controller. I'm calculating here the derivatives that are associated with the tank system. I could have done that in vectorized form. I could have done that separately. It's just, those are the derivatives, there you go. And then I'm integrating those derivatives. So on a very basic level, that's all I'm doing. Yes?
So you're not accounting for dead time in this?
In this particular one, there is no dead time, no. But you will remember that we did simulate dead time systems last year as well. And that just involved looking up into the past. So where that is, there's an example of something like this over here. Here I have an example of a couple of systems in series, and here I have those systems in series with interpolation to resolve the dead time. And so, again, if you understand what is happening here, what is dead time, what is delay, it's just, well, this thing is not this thing right now, it's this thing 2 seconds in the past. But if I'm writing my own simulation while I'm developing that list of things in the past, I can just look at things in the past. Okay, so again, even if you just copy and paste, you'll be able to successfully simulate a system with dead time closed loop. No problem, because it's no different. If you're just using the loop, if you're just using Euler integration, it is literally exactly like. So I hope everybody sees that that little piece of code should look very, very familiar. So there's my diagram. And now I want you to follow the through line of this conversation, right? We have really operational needs here, right? Like this, I'm not doing this because I have some kind of high idea of beauty or whatever. This is like, I'm teaching you how to tune PID controllers. The book has these diagrams showing step responses. You maybe want to see what the step response is going to look like. You want to be able to do that even for systems that have dead time, even for relatively complicated systems. And ideally, you don't want to have to take all the time and draw the diagram in Medallica, which is a very useful exercise. I'm not like, I love Medallica. But how does that interact with Python? Is there a way that I can get roughly the same benefits of being able to build a simulation easily in Python, but in a way that I can call, I can like parameterize, I can write a program that makes a diagram and so on. And so this is where Bloxim comes in, right? So I'm just going to do this from TB control, import Bloxim. And so basically what we have in Bloxim is a couple of different blocks. I'll be building this out, but the most important block for systems is an LTI block. So if you do this, you'll see there's a whole lot of different kinds of things. The things that we are interested in here specifically are an LTI system and this thing called PI, which is a PI controller. Okay, so you can take an LTI, and all of the blocks have a name, an input, and an output. So I'm going to call this block GP, and the input to that block is U, and the output from that block is Y. Okay, obviously it's got also to have parameters now, right? I have given you now a delay keyword. And so this is now the first library in Python that you've encountered that allows you to accommodate dead time directly, right? So you use it exactly the same as you would have if you had an LTI model. So let's say you want like a numerator and a denominator, but now you have this ability to specify a delay. And so this now, what that block looks like when it prints itself is like this. So it tells you, okay, I've got a little, I am an LTI block, I represent this block that takes U to Y. GC, I can do the same way. Now I can do, there's a built-in PI block that like already knows what a PI controller looks like, but obviously you could have just specified the coefficients. This one is parameterized nicely because you can basically tell it, so remember it's block name, input, output, and it is important to, it's important to get these right because the code uses those names to figure out what the sums are. Right, so that's GC, and you can see that this PI controller has a KC and tau I. Okay, so now that's a controller, and like this is what the controller looks like. So it says, okay, I'm a PI controller that does this. The key idea behind Bloxim is that you define these blocks, and then you define a diagram which tells you like how these blocks are actually connected together, right? So you have so now you have, okay, I'm going to build a diagram, and that I do with bloxim.diagram, and that diagram object asks for like a list of blocks, dictionary of sums, and a dictionary of inputs. So I'm going to do the blocks are just GP and GC. They can be in any order, it doesn't matter. The inputs or the sums are a dictionary, like I explained yesterday. Which in this case tells me that E is plus YSP minus Y. So E is plus YSP minus y. And so that value for that dictionary is like a tuple, right? And then I've got the inputs. So these are the sums. Well, I can probably do this. So that's the sums, and then I've got the inputs. And the inputs just specify also, I'm going to say YSP, and that's specified as a function that returns, it's a function of time that returns a value. It's useful to do this. So that's just going to be like, now all of these things are assuming that everything starts at 0 and everything like that. So this is now the diagram, right? So there's my diagram ready to go. And I can now just do, I can get a list of times. Now, this will use that list of times also to choose the integration step size, because internally it's using Euler integration. So I'm just going to be generous in the number of time steps that I do, just to make sure that I don't have problems with numerics. But the beauty of this is that now I can do diagram.simulate, and it's working. Yay. Okay, cool. So there you go. So there you go. You built the diagram, you press simulate. It's doing the simulation now. Taking a long time, but there you go. And then simulation results is a dictionary that contains a key for every signal in that diagram. So that so it's got a U, so it's got all the signals that we defined, right? So it's got a YSP, it's got an E, it's got a U, it's got a Y. And I can plot any of those using the normal way of plotting. Right? So that's the whole thing. And now this works for, as near as I can tell, any kind of diagram that you care to put together. It's not super numerically robust, it's just using the Euler algorithm and so on, but you can do this, you can do an IMC structure this way, you can add date time. So this already has date time in it. So if I want to make that a little bit more clear, let me just add more date time here, because that delay is quite small. Let's do like a 50-second delay. You rerun the whole thing. Takes a while. So in my mind, this is equivalent to, at least in conceptual difficulty, to the Medallica version, right? Like you define your blocks, you add all the stuff together, you press simulate, and you don't have to worry about the concerns about how exactly, how exactly does this even work. I can tell you, you're more than welcome to have a look at the code. I'm super keen to accept pull requests, but I would very much like it if you take this for a test drive, but there you can see there's the 50-second delay right there, and you can see how that's affected the results. And so for my money, I definitely haven't found any of the examples or kind of problems in the textbook that do not work well with this system. It's a very, so okay, full disclaimer is I just wrote this sometime over a weekend or something, so it's not super well debugged or anything, and there's basically no documentation right now. Again, accepting pull requests, but it should be kind of okay. So I'd love it if you exercise it and report issues and but this is the key to understanding all the other notebooks. I've rewritten a couple of further down notebooks to use blocks.